Okay, the last section in Chapter 2 deals with something called partial fractions. And we're not going to use these to plot the functions, but we are going to use them to rewrite rational expressions in a different form. It may not seem simpler, but this particular technique is essential to calculus. And if you take calculus, we'll review this procedure again, but we'll do it now, so when you see it again, it'll build upon it. There are 4 particular cases we're going to look at, and it depends upon what you can do with the denominator as far as factoring the denominator, whether you have real roots or no real roots, and if the roots are repeated or not repeated. So we're going to start with the simplest case, and what we're going to do is take a rational function like this and break it up into multiple fractions with a more simple denominator. So this has a quadratic as a denominator. It's a single fraction, but it has a quadratic. What we want to do is we want to make this into 2 fractions, 2 simpler fractions. So we're going to take the original rational expression. Now, if we were plotting this, one thing we'd know is the horizontal asymptote would be 0 because the order of the numerator is less than the order of the denominator. We would factor the denominator because we need to know what values of x cause that to go to 0. So if we factor that, you get x plus 3 and x plus 1. So now that's not the goal here to plotting it. What we want to do is we want to come up with 2 simpler rational expressions where one is the first factor and the second is the second factor. And the whole idea is figuring out what a and b are to make this happen. And really what we're doing is we're kind of finding a common denominator, put this back together, and then figure out what a and b are to make the numerators of the combined fraction equal. So what we would do is to combine these back together again, but in terms of a and b, we would take the first expression and multiply both the numerator and the denominator by the second denominator. So we're going to multiply and divide by x plus 1. And I put parentheses on here so that I know that I'm multiplying this whole thing times this whole thing. If I didn't have the parenthesis, I might think that I don't have to multiply x by this stuff. So it's just to make it more obvious. Okay, so that's the first part. Now we have x plus 3 times x plus 1 in the denominator for this first term, which matches the left-hand side here. And you do the same thing for the second expression, but instead of multiplying by x plus 1, you multiply by the denominator associated with the first term. X plus 3 divided by x plus 3. Now, if we now combine these two into one fraction, so the denominator is x plus 3 times x plus 1. And now all we have to do is figure out what a and b are such that this side equals this side. So you end up ignoring the denominator at this point because they're the same. So there's 2 ways of doing this. One's easier than the other. It's different than if we have quadratic factors in the denominator, but it's easier if we do it this way. So I'm going to show you the easy way, and that's what I expect you to do. So if I were to, well, one way is just to pick 2 values of x, two arbitrary values of x, and then you'd end up with two equations and two unknowns. So let me do that. So this is not the way we do it, but I'm just going to show you. We could pick x equals 4 and x equals 0. And if we plug that into the equation, you get 4 minus 2 is equal to a times 4 plus 1 plus b times 4 plus 3. And if we plug x equals 0 into the expression, you'd have 0 minus 2 is equal to a times 0 plus 1 plus b times 0 plus 3. And over here you'd have 2 is equal to 5a plus 7b. And here you'd have negative 2 is equal to a plus 3b. So you have two equations, two unknowns, elimination, substitution, whatever. Okay. So that'd be one way, but you can be a little bit more, well, it works for any two values of x, but what if we choose the values of x such that this term goes to 0 when I make that choice? So to make this factor go to 0, x plus 1 to go to 0, x be equal to negative 1, and over here we do the same thing here, so we pick the value of x, so this goes to 0, which is going to be negative 3. So then we use these two specific values of x. So you have negative 1, x minus 2 is equal to a times negative 1 plus 1 plus b times negative 1 plus 3. And what happens is this goes to 0, and so this term disappears completely. So you end up with negative 3 is equal to, here we have negative 1 plus 3, so it's 2, 2b. b is equal to negative 3/2. You can do the same thing here. So again, I put negative 3 in for x into the expression. Negative 3 minus 2 is equal to a times negative 3 plus 1 plus b times negative 3 plus 3. And you can see that goes to 0, so the whole thing goes out. And you end up with negative 5 is equal to negative 2a. A is equal to 5/2. So negative 5 divided by negative 2 is positive 5/2. So those are my coefficients. And so my original rational expression, which has a quadratic in the denominator, which was x squared plus 4x plus 3, is equal to 5/2 times 1 over x plus 3 minus 3/2 times 1 over x plus 1. And so these are equivalent to each other. And if I plotted them, I would get the same curve. So that's what you do when you have a case where you have a denominator that you can factor and you have distinct linear terms, meaning they're different from each other. And you judiciously select two values of x such that in one case one term disappears, in the other case the other term disappears, and it's easy to solve for a and b directly. Okay. Now, another case is where if I tried to factor this, the first thing that you would probably do is factor out an x. So you'd have x squared plus 10. And this quadratic factor, you can't factor again. You have two complex roots, two imaginary roots. So I can't factor this into two real roots. So I have a linear factor, which is actually x minus 0 if you want to put it as a factor. So now what do we do? How do you break this thing up? You know, x cubed. Well, let me put it in this form right here. How do you work this kind of problem? Well, you have one term which has a coefficient a, and you divide by this, which in this term turns out to be x. If it was x minus 2, it would be x minus 2. So the linear factor, this factor, has just the coefficient a, and then the quadratic factor doesn't have just a b, it has a bx plus c. You have to have that to get everything to work out right. So you need to take the quadratic factor, set it equal to. Okay, so that's the big difference. Linear factors, you just have one constant in the numerator. For quadratic factors, you have two parts. So we have three coefficients that we have to find. It's not quite as simple as the one we just did. But it's the same basic procedure to set it up. You're going to now take the right-hand side, and you're going to find the common denominator, which is the same as the left-hand side. So to do that, I'm going to multiply the first term, ax over b, by the quadratic term. I'm going to take the second term, which is the quadratic term, and I'm going to multiply it by the linear term. And I'll get, when I multiply these out and these out, I'll get the same denominator as the left-hand side. And then, so what you'll get in the numerator is a times this plus bx plus c times x. So you get a times x squared plus 10 plus, I'm going to move this x to the front, x times bx plus c, all divided by x times x squared plus 10. And that has to equal 2x minus 3 divided by x times x squared plus 10. So now that we have the denominator the same, we can set the numerators equal to each other. And the whole idea here is to figure out what a, b, and c are to make this thing work. And you may think, well, I've only got one equation. How do I figure out what these are? But the reality is I've got three equations that I can get out of this. So what I'm going to do is I'm going to put in this little dummy 0x squared. And multiply these out. So a times x squared is ax squared. A times 10 is 10a. X times bx is bx squared. X times c is c times x. So you just multiply all the terms out in the numerator of the right-hand side. And then you're going to group the terms on the right-hand side according to whether they have an x squared, or an x, or just constant. So I've got these two terms which involve x. So I'm going to have an a plus b times x squared. So that's those two terms. I've got plus cx from this one, and I've got plus 10a. So what you do is you get three equations by matching these up, but you don't match, well, you could leave the x squareds in there, but they're going to cancel out. You got these two match up because they're both x terms and constant terms. So what I do is I usually write x squared, x, and c. So you get 0. This coefficient has to equal those two coefficients. 2, which is multiplied by x, has to equal c, which is multiplied by x. And negative 3 has to equal 10a. So we got that one's the easy one. C equals 2. Then we can do this one, which is A is equal to -3/10. And then we can do this one, which says that B is equal to -A. If you solve for B, move this to the other side, it gives negative. So that's equal to negative of a -3/10. So that's +3/10. So if we kind of go over here and bring that kind of down there, what we could say is we have A, which is -3/10 times 1/x. And then we have this one, B is 3/10, so you get 3/10 times x plus C, which is 2, all divided by x squared plus 10. And I'd probably just clean this up a little bit. I'd have -3/10x is maybe my first term. And if I factor out 10, 1/10, I'd end up with 3x here. And so multiply it by 10, this whole thing by 10, simplifies down to 3x. So factoring out a 10th, I multiply this by 10. That means I multiply this by 10 as well. And it's just an easier fraction because the rational part is separate from this fraction. Okay, so that's how you deal with linear factors and quadratic factors. Okay, so we've covered two cases so far, which is distinct linear factors and a quadratic factor, which has a, well, it's a linear factor with a quadratic factor. So let's just look at some other cases. So we've got repeat linear factors. So what happens in this case is if we factor the denominator, and it's really already factored, I guess the form it would be is if it wasn't factored, it would be x squared minus 2x plus 1, and that factors into x minus 1 times x minus 1. So we factor that, and it's the same factor. So this is really x minus 1 times x minus 1. So what we do here is you have one term, which is going to have the linear factor by itself, and then you're going to have a second term, which has the linear factor squared. And in both cases, you just have a constant. You don't have any x's involved. Try to remember if that's right or not. Pretty sure that's right. The reason I'm hesitating is that if you multiply that out, you would have a quadratic type term. But because of the fact that it's a perfect square, I don't think you have it. So we'll make that assumption. Hopefully I'm right. So what happens is you're trying to get a common denominator here, and the second one already has the denominator as here. Now you might be saying, well, what's going on here? Well, here we have an x in the numerator, and here we don't have an x in the numerator. So this does simplify things because this is a simpler fraction if you just have a constant in the numerator versus a linear part and a constant part. So we don't have to do anything to this. So to get the first fraction with the same denominator as the other parts is you multiply by the factor in both the numerator and the denominator. The second term doesn't get changed at this point. So you can see now these cancel out, but then and you're back to where you started, but now we have the same denominator. So now we can combine those two. Now I'm going to go ahead and write in the left-hand side. So on the right hand side, I'm going to have, or on the right hand side, the numerator is going to be a times x minus 1 plus b divided by x minus 1 squared. So now, just like we did in the previous examples, we can now set the numerators equal to each other and figure out what a and b need to be so this thing works out right. So what you can do is you can solve for b by setting x equal to 1. So that is, so we're going to let x equal 1. That's because we want it the case where x minus 1 equals 0 so that a disappears from our calculation. So that's when x equals 1. So we plug in 1 into the left-hand side for x, and we plug 1 into the right-hand side for x. And what happens is this goes to 0. So you get 2 minus 3 is negative 1. This is 0, so you get b equals negative 1. And then you can find a by letting x equal anything, really. X, I usually let x equal 0, but it doesn't really matter. Why do I let x equal 0? Well, that term goes to 0. So if you do that, you get 2 times 0 minus 3 is equal to a times 0 minus 1 plus b. So you get negative 3 equals negative a plus b, but b is negative 1 plus negative 1. So to solve for negative a, you're going to add 1 to both sides. So if you add 1 to negative 2, you get negative 3, you get negative 2. If you add 1 to negative 1, you get 0. And then the sign, just multiply by negative 1. So you get a, b equals negative 1, a equals 2. And so if we come back over here, our original expression, 2x minus 3 over x minus 1 squared is equal to 2 over x minus 1, because we have a over x minus 1, plus b is negative 1, so just put negative 1 over x minus 1 squared. And that's the answer. So for both, when you have distinct linear factors, so let's go back here. When you have distinct linear factors, you break it up into a over one factor plus b over another factor. And you solve it by choosing x so that each one of these terms goes to 0. And why I chose, oh, this was to show that, yeah, I was like, why did I choose that? That was just to show you that you get two equations and two knowns. But if you judiciously choose x such that this goes to 0 so that a isn't in the calculation, you can solve directly for b. And if you choose x so this term goes to 0, then b is not in the calculation, you solve for a. So, and for repeat linear factors, the same kind of procedure, except you let x equal whatever makes this repeat factor go to 0, and then the easiest thing is to choose the second value of x being equal to 0, such that if you have any linear terms on the left-hand side, they go to 0. Okay, so that's the third thing. And the final one is repeat quadratic factors. So it's kind of like repeat linear factors, except instead of having a and b in the numerator, you have ax plus b in the numerator for the single quadratic. And then you have, yeah, the question is, no, I think actually what you have is, you have a, I was thinking about this. I think it is ax plus b. Yeah, x plus b, and then you have cx plus d divided by x squared plus 4 squared. Yeah, we don't see this very often, and it's very similar to repeat linear factors, in that this is already in the right form. X squared plus 4 squared. It's this one. We gotta multiply the denominator by x squared plus 4 and the numerator by x squared plus 4. And then the second term is already x squared plus 4, so we don't have to do anything with that. Okay, so again, now that we've done this part, multiplied by 1, so we haven't changed the value of this rational expression, but we now have the same denominator, so we can have the right-hand side and the left-hand side, and the right-hand side is going to be ax plus b times x squared plus 4 plus cx plus d, all divided by x squared plus 4 squared. So now we have the same denominator, so then we can set the numerators equal to each other. So what I'm going to do is I'm going to multiply this out, just save one step. So you get ax times x squared, so you get ax cubed. Then you have b times x squared, so you have bx squared. Ax times 4, so that's 4ax, and b times 4, which is 4b. And then you've got the second bunch, which is cx plus d. And that's it, because we're just looking at the numerators. Okay, so what we can do is we can combine these have x's and these don't have it. These are constants. So if we group them according to the order of their exponents. So we've got ax cubed, bx squared, and then for x we've got 4a and c, that's times x, and then you've got the constant part, which is 4b plus d. Okay, now what we have now is we have x cubed terms, we have x squared terms, we have x terms, we have constant terms. So you'll see there's 0 x cubed. So what that says is 0 is equal to a. So the coefficient associated with x cubed on the left-hand side has to equal the coefficient on the right-hand side. Okay, the second one is 2x squared, and then you have bx squared. So that means 2 is equal to b, or b equals 2. So we got 2 of them. For x, we have 1, coefficient of 1 in front of x, equals 4a plus c. And for c, we have 8 on the left-hand side, and we have 4b plus d. And you can see because a is 0, that's going to go to 0. So c equals 1. And here we have b is 2 from this previous step. So you get that. So 4 times 2 is 8. So that's going to say, if you solve for d, get d equals 0. So going back to the original expression, So let me see where I can stick that in there. I'm going to kind of slide it in here. So what we get is 2x squared plus x plus 8 divided by x squared plus 4 squared. So a was 0. So b was equal to 2. So you get 2 over x squared plus 4. We found that c was equal to 1. So we get 1x plus 0. D is 0. Saw that down here. D is 0 over x squared plus 4 squared. So we can take these and get rid of that and get rid of that. So it's just x divided by that. Now from when you get to calculus, what you'll find out is that if I want to do what's called integration of this, I can't do it. There's no way to do it. But there are ways of doing each one of these. So that are the 4 kinds. I'm going to show you the homework right now. So I've got 4 problems, which I think are the 4 different kinds of problems. And I'm going to do a separate video just going through some other examples, just to give you one more example. You can look at the book, see what they do, get some more examples there as well.